Okay, good afternoon, everyone. It's 12:03 at DC time. This is Marcos. Welcome to the Magnetosphere seminar series. Before we begin, I'd like to remind you this presentation is being recorded, so please keep your microphones on mute and send your questions in the chat box. I will read them at the end of this presentation. And today we are delighted to have Dr. David Jackson. Dr. David is Science Fellow and Manager of the Space Weather at the Met Office. He has worked at the Met Office for nearly 25 years. So his background is in the middle atmosphere, which he has studied using atmospheric models, data assimilation methods, and analysis of observational data. Around 10 years ago, he switched his focus to space weather at the UK's, and the Met Office's interest increased markedly in this subject. So his current role is to lead the research to develop, evaluate, and expand the Met Office operational space weather forecast service. Thank you, Dr. David. So please, you can start.
So thank you very much for the kind introduction and for inviting me to give a seminar here. So my role is to manage space weather research at the Met Office. And so I'm going to give a summary, essentially, of our activities. Hopefully I can squeeze that into about 50 minutes. So the contents, there are 5 parts to the talk. So the first bit is, why do we do operational space weather? And the we, I guess, is the Met Office and maybe the UK in general. Then I'll talk about the services and that the Met Office provides for space weather and the models used. The next bit is to talk about our current research developments. And related to this, the fourth part of the talk is to talk about a program called SWMF, which started last year, which is a joint program between the Met Office and UK academia to try to fill some of the gaps in our services and to more smoothly do the transition between research and operations. And then on a related theme towards the end, I'll talk about completing the RTO O2R circle. So that's research to operations and the reverse process of operations to research. So why do we do operational space weather? I guess the next 2 slides are quite familiar, but yeah, I'll go through them anyway, just quite quickly. So if you think about space weather, you might want to think of solar eruptions. This might include coronal mass ejections, or CMEs, solar flares, or solar energetic particle events. And so the definition of space weather is variability of the sun in the solar wind and near Earth space that can cause impacts to human health and to technology. And a lot of it is intimately related to these solar eruptions, so that if you can identify solar active regions and characterize these solar eruptions, and that's a good starting place for doing operational monitoring and forecasting. And of course, the impact of space weather is widespread. Radiation effects on satellites and aviation, both hardware and humans. Solar flares can affect radio communication. Geomagnetic storms resulting from CMEs can cause a whole lot of issues related to scintillation, position and navigation timing errors, satellite drag, and induced currents in the Earth, which cause a disruption to electric power grid disruption, pipelines, and so on. So it's essentially everything that affects modern life. So because of that, the UK puts severe space weather on the National Risk Register on 2011. It still remains there. So you can see that it's highlighted by the arrow. It's a medium high likelihood and moderate impact. So it's fairly high up compared to some other risks. Circled as pandemic flu, which, as you might imagine, is going to be supplanted with coronavirus quite soon on the risk register. So in 2011, the UK community was already aware of a lot of the impacts of space weather. For example, the National Grid, who do the power generation, were very advanced in understanding the risk of space weather. But we thought it was important to characterise the impacts of extreme space weather on UK technology, UK critical national infrastructure. And as a result, the Royal Academy of Engineering commissioned a report in 2013. It focused on a scenario where there was an extreme space weather event, which is like the Carrington event, based on the Carrington event of 1859. And the impacts, assessed impacts, included for the electricity power grids, around 13 transformers in Great Britain would be damaged. 2 coastal nodes could experience power disconnection for weeks or even months, and general voltage instability could cause outages of a few hours in urban areas intermittently. And for satellites, maybe 10% of the fleet could experience some kind of temporary outage. And also the satellite technology would get, or instruments would age rapidly. For GNSS, there may be partial or complete loss for 1 to 3 days, and also there would be some loss of SATCOM and high frequency or HF communications. Of course, there's a need for continual update as technology evolves. This information in this report and subsequent studies are used to continue the assessment that goes into the UK National Risk Register to assess the risk, the continuing risk from space weather. And in fact, the SWMF program, which we talked about, has a new activity which will essentially update the REE report. So as a result of the space weather going on the National Risk Register, the Met Office Space Weather Operations Centre was set up in 2014. The Met Office owns the risk on behalf of UK government. And so what this means essentially is we provide 24/7 operations, we monitor space weather and provide forecasts. It's a national capability supporting a government, military and critical sectors. At heart of this, we do forecasts up to 4 days ahead to meet UK government and industry needs. That includes geomagnetic storm forecasts, flare forecasts, high energy electron events, solar energetic protons, particle events, and also CMAs. So what do our services and the models we use to produce the services look like? So the basic forecast we disseminate looks like this. So twice a day, we put out a text summary. And this version is the non-technical version for non-scientists. So on the left-hand side, you'll see a text summary of what's happened over the last 24 hours and what will happen over the next 4 days. And then on the right-hand side, you'll see tables where we categorized different types of space weather. And then we've identified the probability of occurrence over the next 4 days. So for example, for geomagnetic storms, you'll see levels from G1 to G2 up to G5, and these are just the same levels that SWPC use. And then associated with that, there's, in the example there shown for the severe the extreme or G5 event, then there's a 1% chance of that happening over 4 days. And we do similar things for X-ray flares and electrons and so on. And then we also, similarly, we do a technical or scientific forecast at the same time, which is an example which is here. We have the text summary and we have the tables to give the categorical probabilistic forecast, but we also give a lot of background information in the form of analyses and images and so on to try to describe the picture better. So what do the forecasters use to make the forecast? Well, the first thing they do is to do a solar analysis based on SDO observations. So an example is shown on the top right, and you'll see that what's done there is to analyze active regions, classify active regions using the Macintosh classification, and also to identify coronal holes which are shaded there. And so that gives the forecasters a situational awareness. They have an idea of what's going to happen over the next few days just based on that analysis. If there are any complex active regions, they're identified and they will likely give, or potentially could give, CMEs, flares and SCPs over the next few days. The active region analysis also drives the flare forecast, and the identification of the knowledge of the coronal holes goes into the issued geomagnetic and electron event forecast as well. So in terms of observations, we use solar images and maps from SDO, also stereo and SOHO chronographs and Gong magnetographs. And we have solar wind observations on the Sun to Earth line at the L1 point from Discover and from ACE. At geostationary altitudes, we have from GOES, we have electron, proton, and X-ray fluxes. Nearer the surface, we have surface magnetometer observations of the magnetic field and GPS observations of the electron content in the ionosphere. And in terms of models, well, we have a range of models. So one is WCNLO, which is a solar wind prediction model, but it also includes CME predictions within it. For the radiation belts is a model called REFM, which produces forecasts of the greater than 2 MeV electron fluence at geostationary altitudes. In the D region ionosphere, we produce nowcasts of HF absorption due to flares and SEPs. We do nowcasts and forecasts of the aurora using Ovation, and then we do nowcasts of total electron content of TEC using the Bernese model in the ionosphere. We also use statistical models, for example, a flare model, which is based on Poisson statistics. Simpler models like a solar wind persistence model, which does quite a lot of what NL does, but it can forecast further ahead. And actually, a lot of this is down to knowledge, so that the forecaster knowledge. So that if you look at these, go back to these probabilistic tables, the probabilities are not generally taken from, they're not generally the output from ensemble prediction models. They're largely the assessment of what's going to happen by the forecasters based on their situational analysis and also their experience and knowledge. So one example of a model we use is WCNLO. This model's solar wind is initialized by magnetograph observations from Gong. But also if we identify CMEs in chronograph data, then we analyze that in something called CAT, which is a CME analysis tool, and place the initial conditions within the initial conditions. So in the movie on the right-hand side, you see that erupting feature that goes to up the way, and on the leftmost plots is a CME. The background pattern you can see is Parker spiral rotation, and then the CME initial conditions are placed on top of that. So you see the CME propagation away from the sun. So if the CME is going towards Earth, and that can give us a forecast of CME arrival at Earth. But there are some uncertainties in all of this. So what we also do is we do a 24-member ensemble where we perturb the CME initial conditions 24 times and run an ensemble. So an example of this is in the plots here. So the red line are the observations of density and wind probably by ACE. I think this is 2017, September 2017 event. And the solid green line is the deterministic forecast from NLIL. Oops. And you see the dashed lines are actually the individual ensemble members. And so you can see that by including an ensemble, that gives us more information about the uncertainty about the CME arrival time, and also can help to help us determine whether the CME is actually going to be a near miss or whether it's actually going to hit the Earth. And what my presentation has been trying to show you for the last 3 minutes is we also do forecasts for different planets. So this example is a forecast for Mars, and we also do forecasts based on NLO for Venus and Mercury. This is a service we provide to ESA, European Space Agency, and is, I think, a forerunner of us providing services forecasts at the location of their individual spacecraft. In terms of the quality of WCN, some studies have tried to evaluate it. So on the left-hand side is Riley et al. Evaluated the issued CME forecast, so the forecast that we put on the NASA CCMC CME scoreboard, and it shows that this is the bias in the arrival time prediction, and you can see that the bias is quite low. And this is in hours, but the standard deviation is quite high. We also have plots from NOAA SWPC and GSFC, NASA here, and the performance is fairly similar in all three models. So what we should point out is this isn't the raw WC NLO output here. The CME arrival is based on the NLO forecast, but then the forecasters through their experience know what the biases are, so they tend to tweak it a bit before issuing the forecast on our own service and also to CCMC. Hence the bias is a bit low. To look at the raw model output in a bit more detail, there's this paper by Gonze et al. Which came out this year. And here we're looking at, for all conditions, not just CMEs, the comparison between observed and modeled. This is wind speed here, density, and magnetic field magnitude. So this is observations along the bottom and the model along the top. So ideally, you want all the model scatter plot to kind of have points all along this diagonal. but actually the concentration of points is a bit above it for lower wind speeds, which suggests a high bias for Enlil, and it switches over to a low bias later on. And then for the density, you can see that there's kind of actually a bit of an anti-correlation with the observations, and with the magnetic field magnitude, it doesn't really seem to react to high values. It sort of stays constant. So we have some assessment of the quality of Enlil from these studies. Other assessment, what we do is for the issued forecasts like geomagnetic storm forecasts, we do near real-time verification. So the example here isn't for verification of the actual model like Enlil. It's actually what we put out in our probabilistic categorized forecasts. And so this is an example of rank probability skill scores for the geomagnetic storm forecast for several months in 2016. And this is a benchmark against climatology. And so essentially, if your score is greater than 0, so shown by the green line, then the forecast is doing better than climatology, and the skill scores are the crosses. So you can see that by and large, doing better. And then for each month, the solid dashed, short dashed, and dotted lines represent the 1, 2, 3, and 4 day ahead forecasts, respectively. So generally, day 1 does better than the other days, and day 3 and 4 for some reason do better than day 2. Also, what you'll see though is the long bars are represent the 90% confidence limits. So essentially, the models are not usually significantly better than the climatology, and the day 1 forecasts are not usually significantly better than the other day forecasts. However, it's a good starting point, a good benchmark to build on, which neatly leads me on to research developments. So in terms of looking at the whole sun to earth domain, we try to model and forecast all parts of this domain. And our goal, as mentioned at the bottom, is eventually to produce a coupled sun to earth model or models with data assimilation for enhanced forecast capacity. As you can imagine, if you've got a CME leaving the sun, you want to model its track all the way through to the magnetopause, past the magnetopause, and into the magnetosphere, ionosphere, and thermosphere. You can't do that with one model when you have a couple of models together. So as I kind of hinted at earlier on, we have models which cover different parts of the domain. There's Enlil and a persistence model for the solar wind. There's a flares model. REFM does the radiation belts to some extent. The DRAP does the D region ionosphere. The Aurora is covered by Ovation, and the Bernese model does the ionosphere, but these models are not coupled together. So ideally in the future, we want to move towards a coupled model system. So this is an analysis of what's missing in our sun to earth modeling suite, if you like. And the most obvious thing is there's no coupling at the moment. I just said that. And most egregiously, if you like, there's no magnetosphere model, although we're working on this. So in the little boxes, we've identified what we think are the major research challenges, or the biggest gaps, if you like, in scientific terms, at least in our forecast system. And the ones in bold are the major ones, if you like, and the other ones are also important. So for example, when I talk about CME prediction, what we do is we identify a CME in the chronograph data. We identify its initial conditions, and then we try to track it towards Earth. But what we don't do is try to predict a CME before it even leaves the active region on the sun. So that's a major challenge we'd want to overcome. And then this also wraps into the more general question of what active regions shall be eruptive. Similarly, we don't know which SCP events are going to happen before they happen, if you like. And flare prediction, though, whilst the Poisson statistic methods and others have some level of skill, we could do better. And then, as many people know, when a CME leaves the sun, what's important is the orientation of its vertical magnetic field, or BZ, because that will determine whether the CME gets past the geomagnetic field shielding in the magnetosphere and affects Earth or doesn't. And at the moment, we can't predict that. All we can do is observe this BZ as the CME passes the L1 point and is observed by Discover. So another big research challenge is to try to observe or predict this BZ, or at least find some way of getting a longer lead time on our observations of it. And then when the solar wind does drive the magnetosphere, there's some knowledge from, for example, from the SWMF model about the strength of storms, but maybe not detailed knowledge about substorms. And then if we go towards the ionosphere and thermosphere, then for example, scintillation, which is a really key thing in disrupting GNSS position, navigation and timing, can be nowcast if you have the sufficient observations, but it's to forecast it is quite challenging. So what I'm doing here is I'm looking at the solar heliosphere domain first, and then I'm going to go into the near Earth domain, and I'm going to essentially repeat some of these challenges and talk about what we're doing, if you like. So these are these challenges I talked about before, and the ones in red I'll address a little bit in detail here. So for example, in developments, what we've got is something called CAT-HI, which is like the CAT tool, but instead of just being based on coronagraph data, it also uses heliospheric imagery. And so this can address some of the issues of CME evolution. With the data, you can track CME a bit further away from the sun and a bit further into the heliosphere. And if we're running a 24-member ensemble, for example, we can potentially use this to prune out the bad ensemble members and just focus on the better ones. ADAPT is a data assimilation system which can improve the initialization of the WSA part of the WSA NLO system. It uses data assimilation of Gong and ensemble Kalman filters, so we do believe that should give you some better evolution of the coronal magnetic field. IPS, interplanetary scintillation, these are radio telescope observations on ground. From these data, you can infer the wind intensity in the heliosphere, and also to some degree you can identify CMEs. So that first of all, this is an important backup if the coronagraph data from SOHO and stereo fails, because those instruments are way past their planned lifetime. So this addresses this point here. But also potentially in future we can assimilate those maps from IPS to constrain the state of the NLIL. So at the moment, there's the initial boundary conditions of NLIL are driven by what comes out of WSA, and that's all the constraint they have. Also, quickly, is something we developed with Bernie Jackson at San Diego is what we call IPS TOMO. So it's essentially we can produce the initial conditions at 21.5 solar radii from the sun. So that's essentially an NLIL initial condition. But instead of running that through NLIL, we can run it through a tomography model, which is a bit quicker and easier to run, and we can produce quick forecasts that way, which is relatively good. And so that's a backup, for example, if we really quickly need to introduce something if the coronagraphs fail. And then the final thing is nonlinear force free field models. For example, one we're working with now is called DUMFIG, which is developed at Durham University. And this again is potentially could be quite good at representing the evolution of the coronal magnetic field, because this representation is better suited to representing active regions and the revolution compared to the formulation, the PFSS formulation that's used in WSA. And again, in the paper by Gonzi et al., a whole range of these options, usually driving NLIL, were compared. And so an example, a couple of plots is shown here. There's a histogram of the solar wind speed for 2014 and 2016. This shaded as the observations. And the WSA NLIL operational version at the time is green, so you can see a kind of little high bias. And the yellow and blue lines are the two versions of DUMFIG, one with a full nonlinear force free field and the other one with a PFSS representation, but also being initialized by the ADAPT initialization. And in 2014, it looks like it does really well. However, in 2016, it's almost like you reproduce the same results for a different year and it's not really responded to the observations. So this is potentially promising, but we need to understand what's going on a bit more, try to tune the model a bit more. For the interplanetary scintillation, when we use that to drive NLIL, it was actually improved the detection of high-speed streams quite well, and the correlation with the observations was quite good. But for example, the spread of the histogram, this is the red line here, was a bit poorer. So I mean, there's some advantages of using the DUMFIG model over WSA, and we're going to look at that a bit more in the swimmer program I mentioned. And also there's quite a lot of advantage in using the IPS data to as a backup in case the coronagraph data are missing. In the plot two plots ago, I talked about the absence of any forecast of solar energetic particle events. And this, we plan to address this by using a model called SPARCS, which is a physics-based forecast model. So what it does essentially is you need information about flare observations, and if a flare of greater than M1.0 class is observed, then the SPARCS model will trigger an SEP. And the assumption is that the SEP is traveling through a solar wind environment from the sun towards the Earth, which is got a constant velocity. And 3 simulations are run, one with 300 kilometer velocity, one with 500, one with 700. So you get a mini ensemble of SEP forecasts. And so this is the greater than 10 MeV flux plotted here for September 2017 event for the 3 different winds. I mean, essentially what happens is the basic physics model is quite expensive, and then lookup tables are generated from that. And so it's relatively easy to do a lookup table based on constant solar winds. But if we wanted to have one based on, let's say, the forecast end-level winds, which varies a lot, then that would be a bit harder, but that could be a future step. So we're waiting, actually we're waiting some observation, observed fields from GOES 16, which will give us the flare identification, and then we can move this into operations. And so regarding the challenges nearer to Earth, and the ones in red here are ones we'll talk about a little bit in the next few slides, and then the other ones are in Swimmer, so I might talk about them a little bit later on. So regarding the magnetosphere model, we're going to implement the SWMF model, which is similar to what is used at SWPC quite soon. And so that will attack some of the issue of geomagnetic storms in the magnetosphere based on solar wind driving. In the thermosphere, we have a range of approaches. So first of all, we are beginning to introduce a model called DTM, the drag temperature model, which is a bit like, if you're familiar with NRL MCC, for example, it's a bit like that. So it's a semi-empirical model, but in the future, we will be taking the TIGCM and then coupling it with our weather and climate model, the or unified model, which will be extended up into the thermosphere. So we can try to represent the coupling that way. And then later on, there might be a lot later on, we'll develop a whole atmosphere version of the and then that can fully represent the coupling between the upper and lower atmosphere. So SWMF is, as I said, it's very similar to what is implemented at SWPC right now. There's a global MHD magnetosphere model called BATSRAS. There's an ionospheric electrodynamics model, RIM, and then inner magnetosphere model, RCM. And so this will be driven by real-time solar wind observations from Discover at L1. And so that's regularly fed with those L1 data, and then you can get a regularly updating nowcasts. What's useful for this model is you can also have some kind of representation of the perturbation of the surface magnetic field, which is shown in the plot here from SWPC. And then going on to talk about Swimmer, there's one Swimmer project which is looking at UK models of ground magnetic and electric fields, and its potential application is we could try to drive those models with the SWMF fields to try to identify, try to improve the forecast essentially. So the SWMF should be going operational around about August this year. And thermospheric density service, as I mentioned, the DTM model is a semi-empirical model that gives you forecasts of neutral density in the thermosphere and the exosphere from 120 to 1500 kilometers. That's driven by geomagnetic and solar indices. And an example of an output that we produce for ESA is shown here. This is the density at 200 kilometers. So we already provide a service for ESA, and we're adapting this right now so we can have a UK focused service for our National Space Operations Centre. And then the whole atmosphere model, as I mentioned, well, it would be really good as part of developing this coupled Sun to Earth system to have one model that goes from the Earth surface to exobase. The thermospheric state is important for the evolution of the ionosphere, so it's important when you're trying to forecast the ionosphere. And the lower level driving is important in specifying the details, the temporal and spatial variability of the thermosphere and ionosphere. So what we've done with our model so far is to extend it from an upper boundary of 85 kilometers up to something round about, actually to 152 kilometers. So what you need for this model, at least for the neutral atmosphere, is you need extensions to the radiation scheme to add non-local thermodynamic equilibrium effects, and to extend the shortwave radiative heating calculations to lower shorter wavelengths and to include the far UV and the extreme UV. You need to add thermospheric chemistry. The exothermic heating from chemistry is the thing that really drives a large rise in temperature in the lower thermosphere. You also need to add relevant dynamics changes, for example, represent the impacts of molecular diffusion, which become important above about 130 kilometers or so. So we have already got a model with 152 kilometer LEDs. All the radiation changes I mentioned have gone in there, so it's really comprehensive. But the chemical changes haven't, so we're trying to represent them simply with Newtonian relaxation at the moment. And there's also a bit of lack of stability, so some of the dynamics changes I've mentioned have not been completed yet. So addressing that plus better chemical heating should give us a more accurate model. As I mentioned in the text, we have good accuracy up to about 100 kilometers or so, but less so above. A couple of examples. This is the zonal wind, so that's the east-west wind from a model simulation here, and from a climatology from the Upper Atmosphere Research Satellite. On the left-hand side, they don't have the same vertical scales, so we're trying to make them match up as much as possible. So what's good is you see the slope in the wind from bottom right to top left in both the southern hemisphere and the northern hemisphere. Then you have a change in the reversal on the wind sign from negative to positive for about 80 kilometers. You get that here. But it's not so well. This reversal here isn't well represented in the northern hemisphere, and then the winds at the top are beginning to look a bit too big. So that's where the model's not becoming quite inaccurate. We also compared the migrating diurnal tides in zonal wind from the model with observations from radars. So this example is from Rothera, which is in the Antarctic, and the model amplitudes are in blue, and observed are in orange. And by and large, the agreement is incredibly good, actually. Maybe some months like December, January, and February are not so good, but this is a really good result. So a promising thing to build on. So the next thing I'm going to talk about, so the second last section of the talk, is SWMR. So it's a program. SWMR stands for Space Weather Instrumentation, Measurement, Modeling, and Risk. And so what is it? It's a £20 million, which is $25 to $30 million program that runs for 4 years through to 2024, and the aim is to improve the UK's capability for space weather modelling, monitoring, and prediction. This will include the development and deployment of new instruments and models, and the Met Office was involved in the design of the program. So essentially, what comes out of it will fill gaps that we have in our services. And a key part is building a pathway, a programmatic pathway, but also an IT pathway, to smooth the transition from research to operations. So unlike a lot of research programs which start with blue sky research and they may have an output at the end which may be good for us, actually we're starting from mature research, and the idea is that will then get taken into operations by the end of the program, or close after the end of the program. So because of this, the successful business have already passed some kind of compliancy tests for scientific and IT standards. And as I mentioned later on, we're going to use something called application usability levels to try to gauge progress and try to measure operational acceptance. So within the program, there are a number of projects, and they can be categorized as the green ones are improved modeling, which I'll talk about in the next slide a bit more. And the red ones are improved observations and instrumentation. Again, will be covered in the next slide. Development of an RTO platform to essentially smooth the transition from research to operations. I'll have one slide on that later. And the other one I won't talk about many more here, but I mentioned it with regard to the Royal Academy of Engineering 2013 study I mentioned near the beginning. So this is essentially an updated study of the impact of space weather on critical national infrastructure in the UK. So if we go back to the plot of Sun-Earth couple modelling again, then a modelling project within Swimmer called SWEEP is focusing on improving the forecasting from the sun through to 1 point. And then, as I mentioned before, in terms of the radiation belts, what we have only is an RAFM model, which is a statistical model, or empirical model, which focuses on the geostationary altitudes. So we'll instead, through SAT-RISK, we'll produce improved satellite risk forecasts, which also will be forecast for different parts of the radiation belt domain. And then for the ionosphere and thermosphere, the two projects, SWMR and SWMR-T, will produce improved forecasts for GNSS impacts, high frequency comms impacts, and also satellite drag. If it goes down slightly lower, SWRM gives improved aviation risk forecasts. So the focus there is on aviation altitudes, so upper troposphere, low stratosphere. And then SAGE, right on the ground, is focusing on improved forecasts of ground level current effects. And then to support these, there are improved observations. So Ground Radiation Monitoring Network is really focused on developing new observations in the UK, which they might not necessarily be radiation neutron monitor sensors, but there might be something like that, so that they're observing radiation on the surface. And although that's not aviation altitude, the data can be quite easily used to help the aviation forecasts, and maybe more directly. It's another project where radiation monitors have been flown on satellites to help the measurement of the radiation in the radiation belts, and also radiation monitors have been developed that can be flown on planes for aviation level radiation measurements as well. And then backing that up is another program or another project called S2, which essentially supplies a technical testing program to do lab-based tests of the instrumentation and associated modeling, so you can understand the instrument response. So in the next few slides, I'll give an example of some of the modeling projects, not all of them. So SWEEP, the idea here is to augment the current system that the Met Office has. So you can see that we use magnetographs to produce a chronomagnetic field forecast in WSA, which is the inner boundary condition for NL. So that's used to drive the heliospheric forecasts. And then chronographs are used to identify CMEs using the CAT tool, and then that goes into the NL initial conditions as well, if there's a CME present. So the blue are new models that are going to augment this. So we'll have a range of different models that can augment what we have. And so we can do that in two ways. One is to maybe take the Dumfries model, which I mentioned before in the study that we've done. So if we find that with further study that that's actually better than WSA, that's initializing NLIL and representing the evolution of the solar winds, for example, then we could swap out WSA and then replace it with Dumfries there. And then there's things like HUXT. HUXT is essentially a 1D version of NLIL. It's a 1D MHD model. And so the benefit there is, instead of running 24 member ensembles, as I mentioned before, for NLIL, we can run 10,000 member ensemble. And so the idea there is we could run a cheap version with big ensemble versions and ensemble numbers, that's HUXT, side by side with the more expensive and slightly more sophisticated NLIL model. And so the potential of HUXT is shown here. This is a time series of solar wind. The observations are in red. NLIL forecast is in blue, and then the HUXT ensemble is the grey shading. So you can see that the spread of the ensemble is often matching the observations. Not always so. And then SWMR and SWMR-T improved forecasts for GNSS, HF comms, and drag. And the reason I put those two together is it's based on those forecasts are based on the same system. So that's a thermosphere ionosphere model, which is TIGCM, plus a local ensemble Kalman filter transform simulation system called Aeneas. And so that's already gone through quite a lot of development, so it should be ready for pre-operational trialing next year. And then towards the end of SWMR, it can be upgraded and finalized with further development. So for example, It doesn't assimilate GNSS radio occultation data at the moment, but that's been tested, so that could be added in if it improves forecast skill. They're doing work on the lower boundary conditions and also improve the representation of electric fields within TIGCM. And then sort of more impact-based forecasts, if you like. For the D region, a new HF absorption model has been developed, which will have impact on the forecast we issue on behalf of ICAO for aviation. New scintillation nowcast and potentially forecasts have been developed. And the ANEAS output will also be fed into an improved satellite orbit propagator based on, so that can improve the estimates of satellite drag. And so one example here is, this is a scatter plot again of rheometer observations against model absorption. And the blue dots are from the DRAP, which is the system we use at the moment, which is kind of quite biased. And then the red dots are with a simulation of rheometer included, where the bias is reduced. And so a further development of this simulation system, which we hope be produced via SWMF, then used in operations later. And then SAGE is forecasting and improved forecasting on ground level current effects. One important thing is to extend the UK magnetometer network from 3 stations to 6, so we can actually observe the changes in the magnetic field due to space weather better. The focus is to develop near real-time coupled geomagnetic field, electric field, and grid pipeline and rail models. And also, unlike some of the, unlike some of the studies where we're getting delivered a model and we have to kind of work out the visualization ourselves, if you like, in SAGE have been quite active in trying to engage with us and also the end user for products. So an example is the lead partner here, BGS, British Geological Survey, have already done these maps for the National Grid, the power grid operator in the UK. These maps, for example, they show geomagnetically induced currents over the UK over a particular period. You can see those larger currents over the coastal nodes, as was mentioned before. And so we've got a kind of head start in trying to focus on producing better end user products for different sectors like electricity or gas or rail. I did mention this RTO platform. It's going to be based on AWS, Amazon Web Services, which I mentioned a couple of times in the previous slides. So there's a couple of advantages here. So usually if we do pre-operational testing, then if it's a big model, certainly, we can do a pre-operational testing on our HPC, our high performance computer. But it tends to be, because we have to fight for time on it, then we have to, the limitations, we can only do these kind of pre-operational tests for a month or something. But the flexibility of capacity, if you like, in AWS means that we can actually do long-term suite testing. So for example, if we talk about the system in the previous slide where we develop TIGCM plus data assimilation, once the first version is available in 2022, then our partners are going to run it on AWS for essentially 6 months to a year, and them and us can assess its performance scientifically and also in terms of the robustness of the system. So this is better than what we had before. But I think even better is the fact that we have an operational environment which is shared with the developers, because we're moving over to running most of our operational systems on AWS as well. So the AWS platform that the SWMF partners will see is essentially the same as the ones that we use in operations. And that's hugely better than the situation where a model system will be developed on a local university system, for example. It will work perfectly, it will be handed to us, it'll run in our system, and then we just have loads of problems. So this will smooth out a lot of the transition from research to operations. So I'm not going to go into details of the system design, because I probably couldn't explain the details, but essentially the basic thing is the academic partners will can access through API gateways. They can access ingested space weather observation data, that's real-time data. They can set up a set of built lines that can produce their executables. and then they can run a set of executable environments to run the models that they built in part 2. So they have the flexibility to set up and to run their models, and we have the flexibility to do the same or to verify the models as they run. So the last bit was talking about completing the RTO OTR cycle. So the plot on the right hand side is something that comes from operational metrology in the Met Office, and it's the bow tie, what we call the bow tie diagram. So essentially, a lot of our scientific technological capabilities focus into an operational outcome, like a weather forecast model, and then that goes from a forecast of wind or temperature. It goes out to whatever the users and customers want. So it's a range of requirements which might not just be the same as what comes out of the model. So there's a kind of research to operations that goes from research through to the model through to whatever focus output we want for the users, and then back the way the users will feedback the requirements if that's not good enough. But also there's a kind of inner cycle where the operational part of the Met Office, which is usually the forecasters, should be able to feedback any problems with the model to the researchers, and then that produces these kind of virtual circles of research to operations and operation to research. Because clearly, if it's all going this way, then these arrows, these feedback arrows, are not there. Then they're going to have a lot of unidentified problems potentially, and potentially a few disappointed forecasters and disappointed customers. So I think this is really summarised in this bullet here, and we tend to have quite good links with end users, and they've been involved in specifying the forecasts and the products we're trying to develop. We need to maintain that, of course, but I think we need to also improve the way that our forecasters can feedback to us about any issues with our system. And we've developed something called Swirl, which I talk about in the next slide, to address this. We need to maintain and upgrade current operational forecasting models, and we do that mainly ourselves. I mean, there's an issue in the future about if we have double the amount of operational models due to SWMF, can we still manage to maintain it ourselves? But that's a problem for the future. We continually need to test, evaluate, and improve these models. So one thing that we haven't really done formally, but we're going to do quite soon, is to develop these AULs I talked about, which I'll talk about again in 2 slides' time, to really set the criteria for accepting a new model into operations. We've kind of done this, and from the point of view of with the operational service, and we kind of know what we need, but that's not really good enough for if we're working with partners, for example, in SWMF. We also need to be a bit more widespread in developing the metrics for the individual models we use in the forecast process. So I showed the examples for Enlil, but quite a lot of our other models, we don't really do much verification, certainly not on a regular basis, so we need to extend that. We need to address gaps in current capabilities. What we're trying to do there is what I described in the third part of this presentation. We're trying to do work to improve Enlil, for example, but there are challenges related to resources. The SWMF project, it significantly fills the gap, and this AWS framework I talked about should really smooth out the process so that scientific developments remotely in academia can much more easily, we hope, go into operations in the future. One thing we haven't really mentioned is test beds, which is we haven't really kind of developed the ideas for that, so we need to do more work. So a couple more slides really to go. Swirl is a system where our forecasters, but actually anybody involved in the space weather process at the Met Office, can record their feedback on models, data, IT impacts. So it could be problems, or it could be positive comments actually. That goes into a central repository, and then the science team that I lead reviews this feedback and records potential solutions, and then from that there's a set of actions that we can prioritize. So it might mean that we add some activity to address some of the feedback in somebody's work plan, or it could be we talk to our IT developers about a fairly quick solution. I think the bottom line is that our forecaster voices are now being heard much more than before, and I think I get the feeling that they're kind of quite happy with this feedback process, and are more happy and more involved in the operation and development of our system than before. And then application usability levels I mentioned before. This is detailed in a paper by Halford et al. 2019. So really, if you want to develop an application, whether it's a model or something else, the three phases is a kind of discovery of the basic research and the viability, the prototyping, and then the implementation. And so in Swimmer, for example, we put these criteria for user requirements and IT requirements in the bid document. So when people bid for money, they had to show they were compliant. So essentially, their compliance and the fact they've got money means that they passed phase one already. And then also these people have done quite a lot of system development on their own system. So they'll probably fairly quickly pass the phase two when they really get going in Swimmer. But we just need to be, put in a couple of steps to make sure that they're in line with what we think an operational system should be. And then phase 3, 7 and 8 is really running the system on the AWS platform that I mentioned. So that's evaluation in relevant real world environment, if you like. And then step 9 is when this whole system goes over from the partners in Swimmer to us to actually approve for operational use and then to use it. And that's really, I think, to document that is a really useful way of trying to help our partners understand what we mean by good coding practice or robustness and all that kind of things by trying to document the whole process. So in conclusion, so the Met Office is a UK risk owner for severe space weather, and it provides alerts and forecasts for geomagnetic storms, CMEs, electron and proton events and flares. And it uses a range of models from Sun to Earth, but they're not yet coupled. So the research that the Met Office and in Swimmer is aimed at filling the gaps in our services, and also eventually to move towards a coupled Sun to Earth modeling system. And the Swimmer strengthens the links between Met Office and UK academia and provides a platform for easier transition from research to operations. And of course, in future, that platform might be able to be used internationally. Oops. And as I mentioned at the end of the presentation there, this is part of our developing range of activities to try to close the RTO OTR circle to try to sort of join up our user and forecast requirements and feedback with what we're doing on the research side. So thank you. That's me finished, and I think I might be ready for some questions.
Thank you. Thank you very much, Dr. David. It was a very interesting talk. We have one question from Jason Schuster. And could the new predictions and forecasts from the Met Office modeling like Swimmer I and T be eventually coupled to the magnetospheric model, for example, Batsara's framework?
Yes. This is one thing that I'm not really. It could do. I'm not really sure how it works. I mean, for example, within Swimmer, we're also developing a model called Gorgon, which is a bit like SWMF at the moment. It's a global magnetosphere model, but it in principle, you could run it at very high resolution, and you could actually extend it right down to the ionosphere. So that may be one way of doing the coupling. Whereas excuse me, TIGCM is kind of at the moment, it's essentially you have electric field models which try to represent the driving from the magnetosphere, so they're kind of quite empirical models. So within Swimmer, within those projects, then the idea would be to try to refine those electric field models so they're kind of slightly more related to reality in terms of time evolution and so on, rather than being as sort of broadly climatological models. So I think within Swimmer you could probably move towards what you're saying, but I don't think it would be completed within the project. It'd have to be something that follows on later.
Okay, thank you. So next question is from Kyle. What do you think is the biggest challenge to improving forecasts?
I would say that it's the BZ thing for me. It's trying to forecast BZ so that when I was talking about coupled Sun to Earth modeling, you could do that with the SWMF right now. You could couple it to Enlil, but it's kind of, you have to work out whether that's useful because you don't have any real BZ information in Enlil. So what we plan to do is simply to drive it with the Discover observations L1. But if we manage to crack that problem, then to have some kind of forecast or BZ, or else some kind of estimate maybe from Faraday rotation that gives us a bit more of a lead time. That would really be a big advance. I think that's one of the limiting things at the moment.
Okay, thank you. Okay, this goes close to my question. Is a plan or an idea to include also BY in the prediction of BZ, or like the shear angle or something like this?
Well, depends what you want to use it for. I mean, I think you can do that a bit better than BZ. You know, even the recurrence models actually do quite well for the horizontal magnetic field, and they don't do very well at all for BZ. But we're not really thinking very hard about how to utilize it, I guess. Are you thinking in terms of how to utilize that within something like SWMF? Or something else? I guess you could have the horizontal component, and then you could run an ensemble with different representations of BZ, since you essentially don't know what BZ is. That'd be quite expensive, but you know, that could be a research topic to consider.
I see. Okay, thank you. Anybody else? We still have some time if you wanted to open your mic and speak up. Okay, that means that everything else clear. Thank you, David. Thank you. Thank you very much.
You're welcome. Thank you very much.
So, our next seminar will be on Monday, 21st, and Steve Morelli will be talking about metrics, validation, and uncertainty. So I hope to see you all again. So have a nice week and stay safe. Thank you. Thank you very much.
Thank you, everyone. Have a great week.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye.